Welcome back. Next, we'll talk about deployments of local differential privacy at Apple. Apple is another very high-profile adopter of LDP, and we'll talk about their deployment. These are described in a paper from 2017. I won't write the authors here because it's listed as just being done by the differential privacy team at Apple. Yeah, fun fact, I guess. At the time, I don't think authors at Apple or researchers at Apple were allowed to put their names on publications, their papers, so they're just like a white paper they put up. I think they've reversed this stance since then, but yeah, I think it's kind of disappointing because they've definitely raked in quite a few citations to this by myself as well as many others, because this was a pretty important paper showing that Apple was using differential privacy. Okay, so their architecture is displayed in this figure right here. And so the main thing that we focus on is kind of the LDP thing here, but I just wanted to show you that there's sort of like a few other things, a few other concerns which are relevant just in terms of, you know, making things more private for things that are, again, outside the model of differential privacy, because this does not fully, you know, control every single type of privacy violation. So for example, dropping IP addresses is something which we'd want to do for anonymization. Yeah, there's other sort of random delays based on system conditions. There's an encrypted channel to make sure there's no man-in-the-middle attack. Yeah, random sampling as well in order to add additional noise into the system. Yeah, there's a bunch of things which are meant to sort of control the privacy disclosure, the privacy loss, which are a little bit heuristic in nature for some of them. But yeah, there's various different controls that they have. I'll mention that there was also some criticism of Apple's deployment of differential privacy. There was sort of like a very low level, like you know, kind of hacker like investigation of trying to see what change happens when you change various things and try to sort of empirically estimate the values of epsilon, because Apple, for example, did not release them in some deployments. So there's a paper by Tong et al. Which looks into this sort of thing. So yeah, what does Apple actually do? Many of them that are used in this paper are based around the celebrated count sketch algorithm. So count sketch is a sort of algorithm that first came up in a paper by Charikar, Chen, and Barak Colton in 2002. And this was kind of a very important theory paper, which this algorithm forms the basis of many important algorithms nowadays as well. Kind of what you can say about it is that it's a sort of way of summarizing statistics succinctly in some way, which I won't really get into now. It's useful for, say, counting frequencies of items within a stream, and it's particularly convenient for privatization. That's sort of all I'll say about that. I don't want to get into it too much here, just due to time constraints. But yeah, I'll mention that there's an additional feature of it that's very nice, which was not actually discussed in rapport, and that is the concern of the communication cost. And the communication cost is an important thing. For example, like imagine you're on your iPhone and you want, and sort of Apple asks you for some telemetry, some sort of information about what you've been doing, and you do it privately. Okay, that's fine. But the thing is, they require you to upload, say, like 500 megabytes worth of data. Of course, this is something that you'd be unwilling to do. You'd ideally like the communication, whatever telemetry data they gather, to be as minimal as possible, like maybe just a few bytes, maybe even a few bits or something would be ideal. So there are versions. So this is, in fact, you know, really both in theory and in practice, a very interesting question about how much communication do we require for a local differentially private protocol. And we'll go through an example in the next, when we're talking about the Microsoft deployment. But yeah, I just want to sort of highlight the fact that it's very important to try to limit the amount of communication that the user device has to do, because it might be somehow limited in terms of how much is reasonable to do. So the only thing I want to mention is about this deployment in particular is the fact that Apple has a thing that the rapport thing didn't. For example, let's go back to the rapport deployment and recall that, there was kind of this mapping from values to these Bloom filters. Let's ignore all this privacy stuff, because like all the stuff in this privacy stuff just sort of obfuscates the point I'm trying to get at. Really, you had some string which is mapped using a hash function to this sort of string B, this sort of the non-private representation of the string. So this is nice for going this way, from going to the value to this representation, but it's not exactly the best necessarily for going the opposite direction. Why is that? Well, you can kind of go one way, but you can't go back necessarily, because you'd have to invert a hash function in order to find what inverting a hash function is sort of generally a hard thing to do. Okay, that is not quite precise, because in this it's a fairly low domain thing. But okay, let me just say that this type of hashing operation that we perform here is very nice for going in this direction from the number 68 to this representation here, but going the other way is not something that we can really do very easily. So as a result, if we want to discover, suppose we get a bunch of values, like we'd run our LDP rapport protocol, we find a bunch of strings B, which are very common, and we have a bunch of these things. But the question is, even if we know which of these things are very common, we don't know which true values led to them. So what we'd have to do is we'd have to basically enumerate over our dictionary all possible things. Say maybe try the number 67, the number 68, and the number 69, and so on. And that would sort of reveal different strings B, and based on which ones are frequent, then we would be able to see, oh, okay, that value mapped to a string, which we saw a lot. So just to sort of state this succinctly, you need to know the dictionary of the values, sort of the set of values that you're potentially looking for. It can't really discover new values. So that's kind of limiting. For example, you'd have to look over, let's just say that users of, say, phones or whatever application you're looking at, they're not always going to use words which are recognizable in a dictionary. There might be, say, proper nouns or something, or just slang or short forms or something. So in other words, you need some way of discovering these phrases, these values, which you might not expect, and the rapport system did not give us a way of doing that. One possible way is just to try all possible strings of, say, all possible strings of a given length. For example, if you wanted to discover all strings of length, say 10, then you could enumerate over all strings of length 10. For example, you start with the value A, and then see, what string, like what Bloom filter, what B it gives you, and maybe it gives you like 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, and so on. So you basically check to see if this is a frequent string. Then you go on to the next one. You do A, B, and see what that, and then so on with C, and then with D, and so on. And you can see that there's going to be quite a few strings you have to really go through one by one in order to see which of these privatized strings was really frequent. This is really kind of a drag, and it would take a very long time, prohibitively expensive, and also result in many false positive values for strings that weren't in the data set. So the Apple DP paper, they propose a method for getting around this, which they call the sequence fragment puzzle. And let me try to describe this. I'll describe it abstractly at first, and then I'll give you a concrete example, so hopefully it'll make sense. And you can read the paper if you want sort of more details or more formally how to do it. So there's sort of a two-stage process. The second stage is something that, like, if you want to discover frequencies of words when you don't perhaps know all the words, then there's sort of two steps here. The first is, discover new words and sort of add them to your dictionary. And step two is compute frequencies of words. And this step is kind of this is exactly what we did before. So like there's nothing really like interesting and new in this. I mean, their method has some new things here, but really the sort of key interesting part is how do we do this first step and how do we discover new words? So we're going to discuss how to discover new words, and then we'll sort of just ignore this part just because it's not as interesting now. And so succinctly speaking, what we would do is we would break a word up into short substrings, and then the client would send a random substring of this longer string concatenated with a hash of the overall string, which they call the puzzle piece. They would also send the index at which the substring starts, not privatized. And basically, when these are transmitted, the server will be able to put these together in order to figure out which string/puzzle piece pairs are common. And then we can match these up and find which new words. So this is probably too many details to really for you to have gotten just now. But let me give you an example to show. Suppose that I'm writing the word Waterloo. We're at the University of Waterloo. Like this is, say I'm on my iPhone and I type it all the time because it's a common thing, but it's, say, not in the dictionary. So the way, instead of just transmitting just instead of just reporting that we typed the word Waterloo locally, differentially, privately, we're going to do a few different things. So first of all, there's going to be some hash function f, which takes a word to a number in the range, let's say 0. Yeah, let's just say it's in 0 through 255. So there's a function, a hash function, and we have that f of Waterloo is equal to, say, 42. So we have both the string and the hash. These are sort of things that we start with. And so what we do is we don't just transmit these. What we do is we break up the string into the following parts. Essentially, there are 4 different messages. Let me write it like this. Oh, sorry, not that. So these are the 4 different strings. Sorry, these are based on the fact that we're sending the word Waterloo, or that we have the word Waterloo, we're going to randomly select one of these 4 different messages. So you can see what we did. We broke the word up into 4 different parts, each of length 2 each. WA, TE, RL, and OO. Additionally, what we do is we include the index where the substring begins. So, we include 1 because this is the substring starting at position 1, 3 because the substring starting at position 3, 5 because it starts at 5, and 7 for 7. And the third thing we send is that we send this hash, the hash value of this word Waterloo. So the reason why is because imagine the idea is what we're going to do is we're going to essentially privatize these strings. Like instead of sending only the word Waterloo, what they're going to instead do is send these strings, basically indicating the index, the substring, and the hash, and they'll send one of these uniformly at random. If you have enough users, then you'll eventually get significant quantities of each of these strings, and the server will be able to really reconstruct and find out that each of these are common words or common substrings. So then how do you know really they should go in, these all should fit together? Well, that's where you find the puzzle piece. Basically, the server will notice that, okay, there's a bunch of different substrings, which starts at 1, 3, 5, and 7, which all share the puzzle piece 42. So that allows you to sort of put them together and connect them, saying that, okay, we must have Waterloo. And that spells out the new word that we've discovered, Waterloo. So that's a kind of neat way, in my opinion, of discovering new words. The sort of trick here is why were we able to enumerate over everything? Well, the reason we were able to enumerate over things this time is because we weren't looking over all 26 to the 10 possible, say, length 10 strings as we were here. There would be quite a few here. Here we're only looking at, say, the number of possible length 2 strings, and we also make sure that the hash function maps to a limited range. And so therefore, if you take sort of the product of the number of possible strings and the range of the hash function, you'll see that it's still pretty big, but quite a bit smaller than we were looking at before, which makes this actually feasible with non-ridiculous data set sizes. Okay, so that is all I want to say about the technical parts of the Apple deployment. Let me just tell you about some of the things that they can do with this. One of the really cool things is they were able to discover quite a bit of slang in, they use this for Apple devices, basically looking at words that people typed in, of course, with local differential privacy. So iPhone messages. And for example, it allowed them to discover things like WYD, what you doing, WBU, IDC, sort of abbreviations like this, sort of phrases which are not standard, is typical phrase like bruh and bae. And interestingly, they also found words which were not actually words. For example, things like LOV and the word TH. Now you might find this kind of surprising and weird. What are these words? What do they mean? Well, you'll notice that these are equal to the word love and the, but without the character E on the end. And this led to them discovering, essentially the phenomenon is the following. If you are on an iPhone and you're typing something, then there's a keyboard, and then as you type, there will be suggestions for like the possible words. So let me try to do a very simple keyboard here. There's the keyboard down here. And up here we have sort of suggestions. So like if we're typing in the word the, and maybe the suggestion over here will be them. And the suggestion over here on the left will be whatever you've typed so far, TH, let's say. So the idea is that if you're noticing, the last character that you would type to complete it is the E character, which is right here. But the thing is, they essentially figured out that people had been missing the E and instead hitting TH, which essentially completes the word to be TH rather than the, which was obviously intended. So essentially they were able to discover this behavior just via the presence of significant quantities of these. So I think that was really cool, the fact that they were able to find that out. So that's one example of an application. Another application, which is like very easy for them to demonstrate and kind of got a lot of people looking at it, is perhaps the best known use of differential privacy with Apple, but it's just finding out the frequency of various emojis in both, say, English and French language phones. So you can see even, in fact, how it differs. English, the most common one by a large margin, seems to be laughing until crying, whereas in French you can see they send more hearts and kisses and love related things, I guess. The kiss emoji also makes an appearance here, lips emoji, whereas maybe, I don't know, English people are thinking more of death. I don't know, but these are just a few different examples. There's also other things, including understanding when users do or do not want a website autoplaying. For example, maybe you visit some websites like news websites where the second you go on it, it starts playing this annoying video with sound on, which you really didn't want, so you pause immediately. On the other hand, maybe you go to YouTube and you open a video, and of course you do want the sound playing. That's kind of the point why you went there. So you can see that the intent of what the user wants is very different on these, so that sort of can be used to read intent and try to intelligently mute websites which users typically would like muted by default. This is in the Apple's browser known as Safari. Similarly, trying to determine which websites required high energy or memory in Safari, and trying to understand which health data types are most popular in Apple's health app. So all of these are real deployments of differential privacy, which run on perhaps even your iPhone that you're watching this on right now. Yeah, okay. As a last topic for today, a last deployment, we're going to talk about differential privacy at Microsoft. In particular, we're going to talk about a deployment described in a paper by Ding, Kulkarni, and Yakanen. And this is a paper from 2017. Yeah, we'll describe some of their things, including a 1-bit protocol for mean estimation, and also alternative strategies for memoization, which are applicable in more settings than Rapport was, including the one that I highlighted, for example, which, focusing on, say, asking user their age every day. So algorithms from this paper have actually been implemented in Windows 10, and they're used to estimate the amount of time that users spend in various applications privately. So yeah, today, I'll conclude this by talking about two different aspects of this. One is understanding communication. So let's we've talked about the setting where we want to average 0 bits, which are 0, 1. But let's throw that out and look at a slightly different setting. We want to average numbers in the range 0, m, under the constraint of epsilon LDP. So while we haven't really described it much in this class, the Laplace mechanism is still applicable in this setting. Specifically, if a user has point xi, which is in 0, m, they can transmit yi, which is equal to xi plus Laplace of m over epsilon. And where this m over epsilon comes in, well, essentially this is just using their local sensitivity. The fact that their value can change from 0 to m, well, you can mask it entirely just by adding noise proportional to Laplace of m over epsilon. So then these can be averaged to obtain the following estimate for the mean: xi plus Laplace of m over epsilon. And we can write the error here, mu hat minus mu, which is equal to sort of the average of the Laplace noise. And sort of how big is this error? This will be magnitude approximately, just by looking at this, using the same sort of trick. Each one of these will be of size approximately m over epsilon, and kind of averaging them, this will be of size roughly m over epsilon square root n. So just using the same type of thing, if we want accuracy or error less than alpha, then we need that n is going to be greater than or equal to m squared alpha over alpha squared epsilon, alpha squared over epsilon squared, which implies that error is less than or equal to alpha. Right, so that's sort of a starting point. Let me mention that this is sort of like, this is all optimal. And this was shown in a paper, the paper I mentioned before by Ducci, Jordan, and Wainwright, in the sense that the amount of accuracy you can get, or the rate here, the error you get, and the amount of samples you need, the amount of data you need in order to get this error, those are both essentially tight. You can't do better than that. However, what is not optimal is the fact that this actually takes a fair bit of communication, in the sense that the user has to transmit whatever their value is, plus the addition of Laplace noise, which is about of the same magnitude. So in particular, even let's ignore the fact that they have to send this Laplace noise. Let's even ignore that. If they're transmitting a number which is in the range 0 through m, then they already have to send omega of log n bits. which if you have a very large domain, a very large value of m, then this can be quite a bit of communication. However, perhaps surprisingly, this paper right here, it gives an O of 1 bit, or not even just O of 1 bit communication. It has a 1 bit protocol in terms of the amount of communication. And I'll describe it and we'll analyze it really quickly. But yeah, it's just a simple, setup here. Xi is going to be some value which is in 0, m. And what you're going to do is send yi, which is equal to 1 with probability. It's going to be kind of like an interpolating version of randomized response. But you send this. And 0 otherwise. So you can see that, let's take a look at the extreme value. Suppose xi equals 0. In that case, then this disappears and just becomes 1 over e to the epsilon. On the other hand, if you send xi equals m, then this would sort of give you this, which is exactly e to the epsilon over e to the epsilon plus 1. So you can see the two extremes are 1 over e to the epsilon plus 1 and e to the epsilon over e to the epsilon plus 1, which are kind of just returning to randomized response. However, this sort of smoothly interpolates between the two extremes as well, which we'll see is sort of beneficial in terms of preserving those values. And yeah, based on these values, then the curator will receive all of these single bits from the user. So, okay, first of all, I claim that this is differentially, let's claim a few different things. First of all, this only has 1 bit of communication, which is immediately obvious because the user only sends either a 0 or 1. The second thing is that this is differentially private, and this can also be seen by just looking at the probabilities and the ratio of probabilities changing between when you have a value of xi equals 0 and a value of xi equals m, which are kind of the two most extreme. Then it'll just exactly be the randomized response type guarantee. And the final thing is the fact that the final fact is just that we have to prove that this is sufficiently accurate. So what the curator will do is give the following estimate for the mean. And it's going to be a kind of weird expression, but we'll see why in a sec. And yeah, this is the expression that they can calculate based on these reports that they get. And let's just compute the expectation to see the fact that this is unbiased. So let's just do it out. This is going to be m over n summation. Essentially just pushing the expectation in, we get expectation of yi times e to the epsilon plus 1 minus 1 over e to the epsilon minus 1. And in fact, let's just do this right here. So this can be written as essentially the expectation of yi is just this quantity right here, 1 over e to the epsilon plus 1 plus xi over m times e to the epsilon minus 1 over e to the epsilon plus 1. And what we can see is immediately these denominators cancel. Let's write this out. It's getting a bit crowded here. And this, once we cancel out the denominator, we have then 1 plus xi times e to the epsilon minus 1 divided by m. And minus 1 divided by e to the epsilon minus 1. So the things we'll see is that this plus 1 and this minus 1 cancel out. Those go. This e to the epsilon minus 1 in the numerator and the denominator both cancel out, so that's gone. Here we have m in the numerator and the denominator, so those cancel out. And we're left with this being equal to 1 over n summation of xi, which is exactly the quantity we want to estimate, which is equal to the mean. So we can see that this is an unbiased estimator of the quantity that we're interested in. Yeah, so this shows us unbiased. A little more work shows that, you know, by the Chernoff or Chernoff-Hufting bound, shows that essentially this gets the same error as before. Implies that error is less than or equal to, say, m over epsilon root n, roughly. And this is the exact same type of error guarantee we had before. Implies error less than alpha. So yeah, like just recall that this amount here is the exact same error that we had right here, sorry, over epsilon squared. The only difference is the fact that this time we, you know, only sent 1 bit instead of the previous log m bits. So we can see that we got the exact same accuracy, but a much better communication requirement, which is kind of a very important thing when we're doing differential privacy in sort of practical settings. Okay, as a final discussion in this lecture, let's talk about memoization one final time. So one thing like that we discussed is you know, trying to if we ask the same query again and again, then instead of telling the curator that value again and again, privatizing it independently every time, what we can do is just reuse the same privatizations from previous things. But the reason why this was potentially flawed is because what if the answer changes, but only a little bit? So to use an example, how about the query asking, how much time do you use, say, I don't know, your email client every day? So this is almost certainly not going to be the exact same amount of time every day. In reality, it'll probably change, but maybe it'll be somewhat stable. Say, you know, it'll always be within plus or minus 15 minutes or 30 minutes of each other, and it won't vary too much outside of that. This is something we would want to be able to handle privately, but it's also something that Rapport is unable to handle because, you know, it only handles the case of memoization when the value is unchanged. So yeah, it doesn't handle small value changes. Now, there are a few solutions to this. For example, one thing is to discretize. Yeah, for example, just discretize. For example, if you want to have you know, a time, what you could do is just say discretize into 0 to 1 hours, 1 to 2 hours, and so on. Basically, you know, if any value falls into a bin, then it's just to say rounded from whatever value it falls into to say the center of the bin. Here would go to the center of the bin and something, just to have some sort of representation, show that there's some uncertainty in how much time there is. There's a few downsides of this, like, and it kind of depends. There's a dilemma here in terms of how wide the bins are. So suppose we had very narrow bins, say like each of them was only for 1 second, then we would have like, you know, we would essentially fall into the same trap as before, that we don't handle small value changes. So we can't really handle having many bins because that won't have the privacy guarantee, or that won't handle this fluctuation thing that we want to handle. On the other hand, what you could instead do is create very few bins and make them very wide, But you can imagine that if you have only very few bins, and this is like, say, somewhere between 0 and 4 hours, saying that it's between 0 and 4 hours is not a very informative statement. So there's either, you know, lots of having to re-randomize due to falling in new bins, or having a lot of error in terms of the rounding. Like here, you'll have, say, 2-hour rounding if you error every time if you just round to the center. So in this paper, in the Microsoft deployment, they have a way that provides a randomized rounding scheme, which allows them to eliminate the latter concern. But in particular, they use a very coarse discretization, but avoid the corresponding error. And it's easy to describe. It's not easy to maybe see why it works, but I'll just sort of tell you how to a specific instantiation of their scheme. So what they do first is, so the user at the beginning, they do memoization, but they do oh, sorry, let me take a step back. So again, each user has some xi, which is in 0m, the exact same setting we just discussed before, and we want to transmit a privatization of this. And the curator is trying to, again, sort of average these values in a locally differentially private way. So instead of just transmitting this, what they do is the following. They first, like step one is they memoize. And what do they memoize? Well, first of all, they totally ignore their value. They pre-compute what do I want to say? They pre-compute some values which they denote AI of 0 and AI of m. These are going to be what are these? Well, this is the this is if you pretend their value is val equals 0 and 0, and then this is when you pretend that xi is equal to m. So if you do sort of both of these pretendings and then you run the algorithm that we talked about here, this 1-bit protocol, then whatever values you get will be some pre-computing you do. Again, these are just sort of pretend values. You don't actually use your real data, so these are totally independent of your data for now. The next thing they do is select an offset. And they pick some alpha I, which is in 0 through m-1 uniformly at random. And yeah, they essentially pick a random quantity, which we'll call the offset uniformly at random, which is between 0 and the maximum possible value in the range. And then these are all sort of done before anything happens, and also with no dependence on the data set and their data point rather. Then the third step is actually when the action happens, when query comes. What they do is they do the following thing. Suppose they're asked to report their value xi, then if xi plus alpha I is less than or equal to m, then report AI of 0, and else then you report AI of m. So you can see that this is a very simple algorithm. Essentially, it's kind of hard to see exactly why it works, but you can read the paper if you're interested. The neat thing is the fact that this essentially can handle these types of discretization issues with no sort of dependence on the how sort of coarse the discretization is, and it'll be appropriately private just due to it only requires sort of pre-computing of, say, 2 different values here. Yeah, in particular, this is kind of helpful in order to handle exactly that age query case, which I mentioned before, where the age is answered each day. Well, in if we used rapport, it would be an issue. But if we use the Microsoft solution, then essentially what the curator would see is a sequence which looks like AI0, AI0, and so on many times. So, but then eventually we would start seeing AI of M, AI of M. And the only thing that the adversary would really learn from this, if they were inspecting the sequence, is when the age in days transformed from being imagine the adversary sees this sort of sequence, and then they notice that at one day it changes from AI of 0 to AI of M. Then all they'll be learning is when that particular day, when the user's age plus alpha I went from being less than or equal to M to greater than M. But since, the kind of intuitive idea here is because of the fact that these alpha I's were chosen randomly, then this privatization, this is still private just because of the fact that the randomization of alpha I still masquerades the user's true age. So yeah, this is just sort of a very rough idea, but it's very useful for being able to handle when the value changes by a small amount in a very neat and elegant way. And this is sort of used in rounding of linear programs and sort of the theory world as well. So yeah, that concludes today's lecture. We talked about 3 different deployments of local differential privacy in particular, and saw some of the concerns that people might have when they're doing differential privacy in this type of setting. We also showed when exactly this type of thing can be useful and helpful in practice. So stick around, because next lecture we're going to talk about other deployments in practice and where differential privacy has proved useful and how these deployments kind of differ.